SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. I welcome you to this course Advanced Thermodynamics and Combustions. We are in Module 3 Thermodynamic Property Relations. Till today we covered 4 lectures on this module, and today we will cover the last lecture, that is Joule-Thomson coefficients and liquefaction of the gas. This is in fact one of the practical applications for the thermodynamic functions and relations that we have learnt so far. In this lecture, we are going to learn the Joule-Thomson coefficient, that is one of the vital practical parameter which is used for liquefaction of gases. In fact, gases at certain pressure and temperatures, they are available in the form of gas. So, it is considered as one of the pure substance, but if you want to liquefy, then what concept we are going to use? So, here the word Joule-Thomson coefficient comes into picture, and it is considered as the critical parameters. Now, where this parameter is useful? So, this parameter is useful in a thermodynamic process what we call as throttling. Now, under the roof of Joule-Thomson coefficients, we will discuss about this graphical representations and what we call as inversion curve. Now, after learning all these things, we will try to give the concepts of liquefaction for gases. So, before I start these things, the fundamental thermodynamic equations what we have learned so far, there are 16 thermodynamic relations, basic relations, Maxwell relations, and we used it for phase change process, single phase systems, internal energy equations. In fact, some of these equations will be useful for the definition of Joule-Thomson coefficients. So, that is the idea that these are the very vital relations we are going to use as and when we recall it for any kind of practical applications. So, before you go for this Joule-Thomson coefficients, let us try to first understand throttling process. In fact, we all know what a throttling process is all about in our basic thermodynamic courses. In fact, at some point of time also during the consideration of refrigeration, we use some valve what we call as throttle valve. But the very basic essential fact is that what does this throttle valve do? So, basically this comes under the broad heading what we call as throttling process. So, when a fluid passes through a restrictions, this restriction I mean it a this kind of a porous plug, or a capillary tube means a very small tube, or it can be any kind of valve. Then its pressure decreases, and such phenomena is known as throttling. Then when the pressure decreases, for example, when the gas expands in a turbine, pressure also decreases there, but there we do not call it as a throttling, but here we call it as a work output that we get from a turbine. So, what is the basic considerations that we have here, that during the expansion of gas in a turbine we say it is a isentropic process. But if the process is not an isentropic process, it is something else, and in this case it is a throttling. And this and in fact this isentropic process is a reversible adiabatic process. And when you say throttling, we are trying to reduce this pressure, but at what cost? and what parameter remains constant. So, that is the idea or in which the throttling process is all about. So, the throttling valves are of any kind of flow restricting device that causes significant pressure drop of the fluid without involvement any work, and this pressure drop normally is accompanied by temperature drop. So, that is the reasons this throttling process is a very common phenomena, or throttle valves are mainly used for refrigeration and air conditioning applications. Now, question arises, we are saying that there is a drop in pressures, but what happens to temperatures? Can the temperature always drop or it can increase? So, that is governed by the Joule-Thomson coefficients. So, in fact, we said that in a throttling process the thermodynamic parameter, that is enthalpy of the fluid, remains constant. Enthalpy involves the internal energy plus flow work. So, if this has to remain constant, if you look at this equation, when enthalpy remains constant, that is and if you can expand this equation, that is U1 plus P1 V1 is equal to U2 plus P2 V2. As you can see here in this figure, that we have a tube or pipe and there is a valve sitting onto it. So, in one conditions we are, or we can say, let us say inlet condition is 800 kilopascal 20 degree centigrade, pressure drop may be 400 kilopascal. So, there is a drop in pressure, but what will happen? Can temperature increase? Can temperature remain same, or can temperature drop? So, all these conditions, uncertainty conditions, still are not known to us so far. So, under what circumstances, whether temperature will increase or decrease or remains constant, that depends on the parameter what we call as a Joule-Thomson coefficients. And in fact, in our entire lecture today, we will be concentrating on these particular parameters. Now, let us see thermodynamically how does this parameter comes. So, one way of looking at these things, we define a parameter Joule-Thomson coefficient mu j, change in the temperature with respect to pressure at constant enthalpy. So, the Joule-Thomson coefficient is defined as the change in the temperature with respect to pressure at constant enthalpy. And in fact, this is one such parameters we have come across when you derive this mathematical equations involving thermodynamic relations. And we also know that another term, that is specific heat, which is also defined in terms of H and T, and that is change in enthalpy at with respect to temperature at constant pressures. So, these two parameters becomes vital to form a relationship, and this relationship we can establish from the mathematical functions we have learnt so far. And one such expressions that we have derived from these thermodynamic relations is known as constant temperature coefficient. One is what is called a dH by dP at constant T, dou H by dou P at constant T, which is equal to V minus T into dou V by dou T at constant P. This is one of the relations we have learnt from these thermodynamic equations. Now, if you say the three parameters, that is temperature, pressure and enthalpy, and if these three independent parameters are functionally related in a cyclic manner, then we can frame a equation what is called as cyclic relations, that is dou T by dou P at constant H into dou P by dou H at constant T into dou H by dou T at constant P is equal to -1. In these equations, so far is we know we have defined dou T by dou P as mu j. This first term is defined. Second term is a last term, that is dou H by dou T at constant P, which is known as Cp, and what we do not know is dou P by dou H. So, we can write the Cp is equal to minus 1 by mu j into dou H by dou P at constant T. Then we use these relations here, then after putting this we get a fundamental relations between Cp and mu j as Cp is equal to 1 by mu j entire bracket T into dou V by dou T at constant P minus V. Okay. So, this is a very fundamental relation that we are going to use in our analysis. Now let us go towards this experimental evaluation of this Joule-Thomson coefficients. We mentioned that for a given inlet conditions, when that means when a gas or fluid enters into a throttling device and final pressure and temperatures, we say that final pressure is going to reduce, but what happens to temperatures? So to do that, we can do this control part in a regulated manner, in a precise manner. So what we do is that we consider a gas that which enters into a systems and it is passing through a porous plug and followed by a valve. So basically the conditions of the gas which is at the inlet or fluid which is at inlet is known, that is T1 and P1, and condition at the exit, that means exit pressure is regulated by a valve and that P2 is regulated by this valve. But inlet condition is fixed, exit condition P2 we are fixing it, and at that P2 what is the temperature we are going to measure. So basically we have a set of data, and that means gas passes through this porous plug, and for a given set of initial conditions and for a given outlet exit pressure we are going to measure T2, and such process we can define this in a graphical form. So for example, in this particular graph you are starting with initial state T1 P1, that is this point 1, another point, that means for another P2 we have subsequent T2. So we say for same initial conditions you have one set of data P2, T2 and P2 and T3 and P3 and so on. So we can generate these data points on this pressure temperature curve and keep on doing this. So this is at one particular inlet state. Now we can change this inlet state to another value. So when the inlet states are another value, so different set of curves can be formed, that is inlet state A, B, C, D, E and so on. So for many inlet state, corresponding exit state we can plot it. But what is more important here in that in this form, you for each of this curve there is a parameter what is called as dou T by dou P at constant H. This parameter we are going to measure for each of this curve. And one the characteristics features of this all these curves is that it's their isenthalpic curve and it is the locus of all the points representing equilibrium states of same enthalpy. Now when I calculate the slope for this isenthalpic curve, and we call this as a Joule-Thomson coefficients, and this value can take a positive number or it can take a negative number or it can be 0. Now what is the characteristics of the curve? That when I say positive to negative number, that means there is a inversion, that means negative value to positive value means it passes through 0 and there is a inversion. So for each of this curve there is a state of inverse point. So that means for each initial state of this curve we can in fact join all these points where there is a inversion. For example, if I am on this curve and I am moving towards left, that means if I am going in the direction of decreasing the pressure, we can see temperature first increases, then the temperature followed by drop in temperatures. So when mu jet is less than 0, the temperature drops, and when the mu jet is greater than 0, the temperature increases. And this particular curve and the states point we call this as a inversion state. And one of the other important aspect of these curves is that if you look at this particular figure, the topmost figure, if you look at, there is no inversion point. So decrease in pressure will always increase in the temperatures. So there is no state of inversions. That means for this particular situation we do not have any inversion point. So we can say that the uppermost curve has always a negative slope, which means throttling of the gas from its initial state, for that means for this case on this curve would result in increase in the temperatures. And for the states right to this inversion curve, the value of Joule-Thomson coefficient will be negative quantity, and that means the temperature increases as the pressure of the exit of the apparatus decreases. For the states to the left of the inversion state, that means if you fix this inversion state, anything you go towards the left, what is going to happen? The temperature decreases as the pressure at the exit of the apparatus decreases. So, this concept gives to the fact that we can take this advantage that temperature can decrease as the pressure of this decreases. We can use this concept to as a liquefaction of gases. We will see more details towards the later part of this lecture. Now, let us understand more closely about this inversion curve. So, we are now going to introduce the inversion curve, or we can say inversion lines. So, a more clear picture what I can say that from a fixed initial condition P1 to P2, we can get a varied conditions P2 and T2, and we can put these curves in this manner on a temperature and pressure diagrams. So, when we say mu j less than 0, temperature decreases, mu j is equal to 0, temperature remains constant, with mu j greater than 0, temperature increases. Now, what you do is, this is one set of the curve for a given initial states. For different initial states like A1, A2, A3, A4. So, for all these are what we call as initial states. We can locate the corresponding state point 2 on each of this curve, okay. And for each of this curve, we can also locate at what point this mu j is 0. So, that is the maximum point where mu j is 0, that is slope is 0. So, once you locate all these points, then we can see from this curve, typically for this curve, for the curve A3 we have this point, for the curve O2 we have another point, for the curve A1 we have another point. Now, and for one of the curve we can have another point on the temperature axis itself. So, likewise if we can draw a continuous curve joining these points, this line we call this as a inversion line, and many times we call this as also inversion curve, and this is the line where we can say enthalpy is 0. So, it is the temperature at a point where the constant enthalpy line intersects the inversion curve is known as the inversion temperatures. So, basically these are constant H lines and it intersects this inversion line at this point, and we call this as a inversion temperatures. So, if you drop this particular line on the temperature axis, we can say these are inversion temperatures. So, these are known as inversion temperature. And one interesting fact is that this inversion temperature for the ordinate, that means when P is equal to 0 line, that is on the temperature axis, at this particular point this P is equal to 0, and this is known as maximum inversion temperatures. Okay. This is another some of the physical interpretation also we can say that the throttling process proceeds along the constant enthalpy line in the direction of decreasing the temperature, that is right to left. Temperature of the fluid will increase during throttling process that takes place right to the left side of the inversion line, while the temperature drops in the left side of the inversion line. That means, if this is your inversion line and this is we are moving towards right and we are moving towards left, and when you move from right to left, that means when you are moving from right to left, then the temperature increase, and when the temperature drops in the left side of the inversion line. It is also evident that the cooling effect during a throttling process cannot be achieved unless this fluid is below the inversion temperatures. So, in fact, this is a well known fact that, for example, if you look at this topmost curve, and this topmost curve does not have a mu j value which is equal to 0. So, it does not have this inversion curve. That means, starting from this initial state, we cannot achieve, we cannot reach a value for which mu j is equal to 0. So, that means, if you are starting from this curve, we cannot reach this inversion line. So, if you are not reaching this inversion line, it is quite clear that you do not arrive, that means you cannot achieve cooling during throttling. So, this particular concept, let us see that how this inversion curve is useful for certain fluids. Now, the fluids that are much of importance is like hydrogen, many a times you use liquid hydrogen, liquid helium. So, basically heliums and hydrogen, they are available in gas form, but we store them in the liquid form. Now, while storing them, you can see that, for example, you have to find out there with their actual values of pressure and temperature, we have to draw first this inversion curve. So, this typical picture shows that the nature of inversion curve for hydrogen, another curve gives it for helium. So, for instance, if I say this, for example, if you say the maximum inversion temperature of hydrogen is minus 68 degree centigrades, which means this is close to about minus 68 degree centigrades. That means if you want to get the cooling effect, so that means if you cool hydrogen, then only we can liquefy it. That means your throttling process should start anywhere which is below on this line. So, all this throttling process, the state points, initial state point, which has to happen from any of this thing, any of this initial state. So, that during throttling process we can reach into this inversion curve so as to get the cooling effect. Now, this particular concept is extended for liquefaction of gases. Now, one of the important consideration for liquefaction of the gases that we should get the cooling effect. So, means cooling through Joule-Thomson expansion can be achieved if the initial temperature of the gas is below the point where the inversion curves intersects the temperature axis, that is below maximum inversion temperatures. That means if you want to have this cooling effect, then we must be within this region, within this inversion line. But if the initial temperature is above the maximum inversion temperatures, so this, for example, if you have this maximum inversion temperature is this for this for a given gas, then your initial state should be much above, and if you have above this, then we cannot raise the temperature. If the initial temperature of the gas is above the maximum temperature, then Joule-Thomson effect will raise the temperature of the gas and liquefaction is not possible. And another point I need to emphasize that there are certain advantages of this Joule-Thomson coefficients, because this Joule-Thomson coefficient to produce liquefaction of gases has many advantages. Few of them are like this. First one is the larger temperature drop for a given pressure at low temperature. That means when you are dealing this, when you are looking at the gas at low temperatures, for a given pressure drop we can also get the larger temperature drop. That means when you do this throttling process at low initial temperatures, we can get a larger drop in temperature for given pressure drop. And moreover, here we just have to reduce the temperature, there is no moving part. That means the other issues like lubrication of the devices is not required. So, these two advantages helps us using the concept of Joule-Thomson coefficient as a mechanism to liquefy the gases. Now, let us understand with respect to some realistic number, how I should approach while doing this liquefaction process. So, you can recall our previous figure as if that we are having a throttling process which is happening through this mechanism in which we have some inlet gas. So, if I say this inlet gas which is entering to this throttling device which is at the state P1 T1 and exit state is regulated by a valve, that means we are regulating pressure P2 and finding the temperature T2. Now, what our given situation here, that we have the initial state would say 1 mole of gas, and here I say its initial condition is Pi, Pi and Hi, and its molar enthalpy of Y unit of emerging fluid, initially it is in gas state, and in the outlet we are getting this exit, we have two parts, one is liquid and we have other is gas. So, 1 mole of gas if it is entering and we are getting y unit of liquid, that means y mole of liquid, and so that 1 minus y mole of gas. So, in the gas phase we have 1 minus y mole, and the liquid phase we have y mole, and the conditions that we are getting in the liquid phase is PL, and it is governed by its saturated temperature and pressure, TL and HL, that is enthalpy of saturated liquid. And for the gas phase, that is for which 1 minus y mole of gas is being produced, so we have Pg, Tg, that means saturated temperature of the gas, Hg. So, these are the saturated values. Now, if I say this, the fundamental equations, that is initial enthalpy, will be equal to y times enthalpy of the liquid phase into 1 minus y times enthalpy of gas phase. So, this equation can be formed that y is equal to Hg minus Hi divided by Hg minus Hl. So, this is a fundamental equation normally we use in the stream table as a dryness fractions, but here we are interpreting this y as a amount of liquid that comes out. And now, here in this equation if you look at closely, the values of Hg and Hg is limited by the conditions at the exit stage, that is saturated pressure and temperature values, and that is again is fixed what condition we are exiting this gas and liquid, and even liquid state is fixed by its own saturated state. So, we do not have much control of Hg and Hi, but what we have is we should have the initial situation Hi. Now, where I should start my initial enthalpy? That means we need to liquefy. If you want to liquefy this gas, that means we need to have more and more quantities of y, then we need to maximize y. So, for maximum y we should have minimum value of Hi from this equation. Then one condition you can impose, because in this process what is going to happen, we can write this equation that enthalpy of dHi by dP, because we are regulating this pressure at initial condition Ti, T is equal to Ti, should be equal to 0. Now, this equation can be expanded as dH by dt into dt by dP at this is equal to 0, and through this cyclic relation between H, P and T, and from the by definition we can say it becomes minus mu j into Cp is equal to 0. Now, Cp for this gas cannot be 0, so one condition you must have that mu j should be 0. So, in other words, in order to liquefy for a maximum quantity of liquefacions, we must start the initial state should be fixed for a conditions where mu j is equal to 0. So, this is the starting point. In fact, that we also proved that your inversion you should start the initial state for which the state should be lower than the inversion temperature in the curve. So, this is the very basic bottom line for liquefaction of gases. And now, in the end I will just try to give some realistic number. What is the significance, that means why we require liquefaction for certain gases. One thing in this picture you can say that maximum inversion temperature for helium is 43 Kelvin, hydrogen it is 204 Kelvin, nitrogen is 607 Kelvin. But this is what we say, all these numbers and all these for hydrogen and helium they are much more below this room temperatures, whereas for nitrogen we can get a cooling effect without, there is no issue of initial state, because its inversion state is maximum inversion temperature is 607, that means they are much above the atmospheric and these are much below the atmospheric conditions. So, what does this signify? If air is compressed to a pressure 200 atmosphere and 52 degrees centigrades, then we throttle this air to 1 atmosphere, that means we are reducing the pressure. Subsequently, for this initial conditions the air temperature will be reduced, and this reduced, that means we get a, in this case, a cooling effect. But when you do this same thing for same initial conditions for helium, this temperature will rise, that means initially it was 52 and this temperature will rise, that means we cannot achieve this cooling effect for helium, but same thing we can get it for air. So, this is the significance of how different gases behave. when you start from its initial state. So, that means for many gases room temperature is already below the maximum inversion temperature, so that no pre-cooling is necessary. Now, once the gas has been pre-cooled to a temperature lower than maximum temperature, the optimum pressure to start the throttling corresponds to the point on the inversion curve. Now, there are some issues, like if you want to store this hydrogen or helium in liquid form, then people try to use is that hydrogen is generally pre-cooled with liquid nitrogen to achieve its initial state, and helium is normally pre-cooled with liquid hydrogen to achieve its initial states. So, for certain these cases there is a challenge that how you are going to store them in the liquid form. Okay. So, with this I come to the end of this lecture, and towards the end I will just try to solve a simple problem. It is not actually, most of this content of this lecture are more towards the physical natures, but many times we use the word so that the Joule-Thomson coefficient for an ideal gas is 0. So, in other words, it means what will happen if I use a throttling process to lower the temperature for an ideal gas. Can you throttle it? If at all I throttle it, what is going to happen? This is the physical significance and or physical consequence, but the very basic bottom line that we should give our attention to Joule-Thomson coefficient for an ideal gas. What is happening? And this number will tell you whether we can throttle an ideal gas or not. So, to start with, we can recall our fundamental expressions that we derived, that is between specific heat and mu j. So, we say specific heat Cp is related to mu j as 1 by Cp, or we can write mu j is equal to 1 by Cp into T into dou V by dou T at constant P minus B. This is one of the expressions that we derived in this lecture. Now, for an ideal gas, we have these relations P V is equal to RT. So, we can say dV by dt. So, this will tell you V is equal to RT by P. So, we can find out dV by dt at constant P, this will be R by P. Now, when I substitute this, we can write mu j is equal to 1 by Cp. Now, T into dV by dt is R by P minus V. Now, RT by P is nothing but V. So, I can say 1 by Cp V minus V is equal to 0. So, we say mu j is equal to 0, and this mu j means dt by dP at constant enthalpy is 0. This is we are going to achieve through throttling. And throttling happens at constant enthalpy. What happens if you drop the temperatures? This makes us the understanding that in a throttling process, since mu j is equal to 0, the throttling process cannot be used to lower the temperature, but it can lower the pressure, but the throttling process cannot be used to lower the temperature of an ideal gas. So, this is the fundamental concept for the Joule-Thomson coefficients. With this, I come to the end of this lecture and also I come to this end of this module. Thank you for your attention.